Okay, the last of the three projectile motion discussions that we're going to have is regular projectile motion where with two scenarios. One in which you're right on the ground and you're shooting a cannon or a bullet or whatever up. Well, you're not going to shoot a cannon up because who can shoot that well? Shooting a cannonball up. And the other one is starting on a platform or a cliff or something and shooting up and then calculating how far it goes. Okay, so that's what we're doing today for this one. So we're going to look at those two perspectives. First one, the cannon is shot on a flat surface at 350 meters per second at an angle of 30 degrees. How far or how high and how far will it go? Okay, so we do need the time, and I'm not asking specifically for the time, but you have to figure out the time for this. But the difference from this, from the last one we did, but similar to the first one we did, is I want to find out how high it's going to go. And then the second part was the same as the last time, last one, but not the first one, is how far will it go. And again, we're trying to find the time, but you got to be careful of the time because the first calculation is going to deal with the vertical aspect, just like we did with the last one. How high is it going to go before it starts dropping back down? That's the question. So that means that since we're starting on the ground, it's going to hit and then come back to pretty much the same height from where it left. It's going to be double the time it took to get to the height. So we're going to calculate the height, the time it takes to get to the height, and then we are going to double that for the total distance going across. Okay, so let's start with this, and you're going to see a big change over what we've done with the last two and how we start this. So you've got your level ground there. That's about as level as most grounds are. My ground light in my backyard is more, because I swear my house is sinking, my whole yard is sinking. There's something going on underneath my house. By the way, you want my house? It's really nice. Anyway, so we're going to shoot the cannon here at an angle of 30 degrees. Now, again, we have to remember, like I said last time, once it leaves the cannon, the cannonball starts to drop. It doesn't go in a straight line up. It'll initially start just as it leaves the mouth of the cannon, but as soon as it does that, gravity takes over and starts pulling it down. So you've got these contrary forces working here. So what we're going to have to do with this is we're going to have to look at this as if it's a right triangle as it leaves. We're going to assume the instantaneous moment at which it leaves the cannon, and we're going to look at the vertical velocity and we're going to find the horizontal velocity and use those two values to figure out what we're trying to find here. So we have here a right triangle. So this is V, vertical velocity. This is V, horizontal, VH. And this is VA. This is the actual velocity that it's taking off. And we said that this is 350 meters per second. Now that's at this oblique, this is called an oblique angle, or oblique vector, because it's not perpendicular, it's not 0 degrees, it's somewhere in between, so that word we use for that is oblique. But we have to find these two components based upon that. So this is where we get to use our good friend, Caroline. Repeat after me. SOHCAHTOA. SOHCAHTOA. So, if I need to find VV, and that's opposite the 30 degrees, and I have this, which is opposite the 90 degree angle, so we call this the opposite, we call this the hypotenuse, and this VH then is going to be the adjacent leg of the triangle to that 30 degrees. And since we have the hypotenuse, and we're looking at opposite, that's going to be the SOH, the SO in SOHCAHTOA. So that means then that the sine
of 30 degrees is equal to the opposite, which is our VV, over our hypotenuse, which is 350 meters per second. Well, this is a really easy algebra problem. So all we have to do is multiply by 350 to get it over the other side. So that means then the vertical velocity then is going to be 350 sine 30 degrees. And I just happen to know this because the sine of 30 degrees is always equal to 1/2, so the answer is going to be 1/2 of 350, which is going to be 175 meters per second. So we know that the upward velocity, beginning upward velocity, the initial upward velocity is 175 meters per second. Now we do the same thing with finding the VH. Now, if you notice the VH is the adjacent, and we're going to use the known quantity that's given to us, 350 by hypotenuse, and that is ka. For those of you who have ever seen a wonderful movie called A Fish Called Wanda, ka comes into play very importantly in that movie. Ka. So we got cosine of 30 degrees is equal to, now it's VH over 350 meters per second. Again, a very simple algebra problem here. By the way, that's Monty Python people in the movie, so you know it's going to be very funny. So we multiply 350 by cosine 30, so VH is 350 times the cosine of 30 degrees. Yeah, I don't remember that very well, so I'm going to have to check that one out here. Let's see, we found out that that is VH, where are you at? VH. Oh, I didn't do it yet. Okay, it's down here. VH is 350 times cosine. That's 303 meters per second. I guess I did it kind of differently from what my script was, but ain't no thing. So that is 303 meters per second. Yes, we're going to use that later. That's why I have it so much later in the script. So, but I'm just establishing the two components where we talked about components of vectors before I did the throwing up physics thing, and how we have to separate it into a right triangle. That's what we just did with that. But this is the part we're going to deal with first, because we need to figure out how much time we're dealing with here, and to figure out how high it goes.